that, and we minimize that. Interesting. So it looks like my audio has been muted somehow, because it should have told me that it started recording. I didn't hear it. There you go. Looks like my sound was turned down to 0.
Can you hear us now?
Yeah. See, I found out. I don't know what turned the sound to 0. Something turned my sound to 0. Yeah. So that solves the mystery. Okay, very simple problem and a simple solution to the problem. All right. So today we're going to talk about the temperature dependence of the rate or the rate constant. Okay, and then we will talk about the mechanism of a chemical reaction. What do we mean by mechanism, and how do we go about establishing that? And so these are the two topics today we're going to cover. And the section on enzymology is not included in the exam, and because we don't have time to cover that today. And it won't be fair for me to ask you to cover by yourself. So we will take it up after the exam. And so we have to make some bit of an adjustment there. So other than that, everything covered till today's class will be on the exam. And so we will see how the temperature affects the reaction in a very conceptual way first, and then quantitative way. So the way to understand the temperature dependence of a chemical reaction is to examine what are called one-dimensional surfaces. So what these are, potential energy surfaces that are plotted as a function of internuclear distance. That means you have, using quantum mechanical calculations, you can calculate the energy of the system at various distances between the particles. Say you have a hydrogen molecule, you have 2 atoms, and then as these 2 atoms approach from infinity to the equilibrium bonding length, bonding distance, you can calculate the energy as at all these different distances that you want, and then you can plot that. By plotting that, you show energy versus the internuclear distance. So that is exactly what I'm showing here, essentially, but it's slightly more complicated than just that. And so that is a one-dimensional potential energy surface. And we can now do that kind of calculation if a hydrogen atom is approaching a hydrogen molecule. So now there is a reaction, H plus H2, giving rise to H2 plus H. So this is a very well studied and understood simple chemical reaction in reaction dynamics and simulations and so on. Way back when, 40 years ago, we had a speaker who came in and talked about this in great detail, how they have done these calculations. H plus H2 goes to H2 plus H is a chemical reaction. And so you have a 3-body problem, and this is solved very nicely and approximately, of course. And then you simply collect the energy versus internuclear distance or the positions of various nuclei. Usually, we're going to look at the internuclear distance of the bond that is breaking. Whatever bond we know is breaking, that's the distance we are going to study in this. I mean, you can study any parameter. You could study angles, you can study lengths, you can study other parameters for the reaction and plot that. And so you can develop a very detailed multi-dimensional surface, and which is hard to understand. So we simplify this into a one-dimensional problem, and so put that as a one-dimensional system and then move with it. So what I have shown here is energy on the y-axis and the distance between the 2 nuclei that are separating when the bond is breaking, or when coming together when the bond is being formed. That's the distance we are looking at. That's on the x-axis. And there are just the positions of the nuclei. There's not the electron positions, but the nuclear positions. And then you calculate the energy of the electron as the system is changing this way. And so I have drawn some schematic line showing that there is a well, and then before the well, the reactants have to cross over. Certain reactions are somewhere on the left-hand side. I haven't shown that, only I'm showing the well of the product. So they have to cross over certain barrier to give rise to the products. This is just a schematic, and I will explain why we do this sort of thing and why not a different kind of thing, et cetera, et cetera. And then the potential rises very steeply past that internuclear distance if you go further out. And usually it doesn't work this way. It's actually flipped backwards. But anyway, it's just a question of a schematic. Just draw it like that and see some hypothetical case. Don't take this literally. So the arrow here shows that the reactants have to go to the products over a certain barrier. So that's the basic concept. And the rate constant in this scenario is defined as the probability that the reactants go to your product. It's just a probability. There's nothing really else to it. Of course, we have units associated with those, first order rate constant, second order rate constant. They all have different kind of units, etc. And so in a sense, it is the probability that we are talking about. And then as we change the temperature, the probability is changing. So that's the thing what we are really interested in learning today. So because the rate constant is essentially related to the probability that a reaction might occur, that's by definition by occur, it cannot be a negative rate constant. And so there are some people who publish negative rate constants in the literature without understanding this. And so they made a huge mistake and they had to retract their papers after publication. So this is a fundamental mistake, and whatever reason, how they got the negative rate constant, I have no idea. But rate constants cannot be negative, and it can be zero. That's the point. So the highest point that the reactants pass over to give products, by definition, the saddle point. So it's like a saddle on a horse, and you sit on a horse. The highest point on the horse is your saddle point for sitting. Of course, the head is higher than this, but so that's for whatever reason, somebody introduced this into physical chemistry, saying that this highest point is a saddle point, and in highest point in energy, and there are many paths. In other words, I can draw many such one-dimensional diagrams, and among all those one-dimensional diagrams, the one that has the highest crossing point is the highest activation energy system, and the system will follow through that. But the system will follow through the lowest saddle point. So every line will have a saddle point like that, but the actual thing that the system crosses over is the lowest point. In other words, the lowest pass through a mountain range. There are many, many passes, but the pass that's the lowest in energy is what you prefer. And that's the most probable path. And so by definition, the rate constant is the probability for the system to cross through that pass, the mountain range, from one side to the other side of the range. And so that's how we look at it. And software modeling allows the prediction of rates, rate constants, and the geometries of the activated complexes, etc., and so on and so forth, and gives the best trajectory. We can predict what is the trajectory for the reactants passing through the product. What does that mean? It means that we can describe the mechanism in great detail, in atomic precision, how the mechanism or how the reaction proceeds. And so this is very powerful, and now it's getting even more powerful because we have really fantastic algorithms and hardware to be able to do very detailed calculations. And so not only we can determine which reactions happen by quantum mechanics, now using dynamics, we can also tell what path is the most preferred path. In other words, what's the real mechanism for a given system. I think it's easier perhaps to determine using computational chemistry than using experimental chemistry, because experiments are very hard to nail down these details. So consider temperature and pressure dependence. We will do temperature dependence. We already did pressure dependence at some point, but anyways. So the reaction rate is proportional to some constant, of course, rate constant, a to the power x, b to the power y, etc., etc. In general, this is how it is, where x, y, etc., the orders with respect to a, b, c, and so on and so forth. Right. So this is what we analyzed in the last class. As the temperature increases, concentration don't change, and so concentration is constant, is independent of temperature. Say many moles per liter, so many moles per liter. Therefore, there should be some other reason why the rate is increasing, because order doesn't change. The order doesn't change with respect to temperature. If the order changes with temperature, means that there is a change in the mechanism. The reaction may be producing different kind of product, or maybe going through different pathways, and so on. So the order should not change with temperature if there is no fundamental change in the chemistry. And the rate constant should change as a function of temperature, because we know the reactions go faster most of the time at higher temperatures than at room temperature or at lower temperatures. There are some exceptions, and we understand the exceptions really well. So from that, we can discuss that a little bit later. But what it means is then that there must be some other reason why the reactions go faster, not the chemistry, not the concentration, not the order of the reaction. So let's say what really changes. The temperature increases the rate, and that is due to some parameter, which we're going to discuss next. So for every 10 degrees, the rule of thumb is that the rate essentially doubles for a chemical reaction. This is really amazing fact. And in a day-to-day life, this plays out very well. Suppose you want to start your car, let's say it's a gas car, and you have to crank the engine up to ignite and start running. So you use a battery to crank the engine up. In the old days, they used to have a crankshaft, and then you do that. Lawn mowers, they have a string. You pull the string to start. Old days. And so what then that is, then if you're using a battery to start your car, there are chemical reactions happening in the battery to run the car. And as the temperature dips, say below 0 degrees, most batteries don't work anymore. And so everybody's asking for a tow truck to come and jumpstart their cars, because the chemical reactions are very sensitive to temperature. So they double for every 10 degrees. Keep this in mind next when you want to start your car in winter. It's really difficult unless you have good quality battery. And in Canada, I was told that they have heaters to heat the either the engine block or the battery. So the battery actually works reasonably well in sub-zero temperatures. And so this is a real problem in real life. And exactly the opposite happens when you cook something, right? You put something in water and boil it, and the temperature goes up, and the hydrolysis of the food to give rise to your cooked food goes faster and faster. It doesn't cook much at room temperature, but once you start heating. And so there's a lot of this temperature dependence of chemical reactions all around us. And the body uses this sort of thing to kill off bacteria when you get an infection or viruses. The small increase in the temperature is enough for the bacteria to die off, or the viruses to stop multiplying. And so body's defenses, just a few degrees Fahrenheit is enough to take care of that. And so anyways, that's all because chemical reaction, biochemical reactions and chemical reactions, and chemical reactions controlled by temperature. And so they can cause problems unless we regulate the temperature. That's another reason body regulates the temperature very precisely biochemically. And so the temperature of the body is a very good indicator of the health of the individual, and so on and so forth. So increase in temperature, increase in the number of collisions, and maybe that's the reason the reactions go faster with increase in temperature. We can wonder about that. But the only problem with that is we showed that the number of collisions happening per second per unit volume is proportional to square root of temperature. So if it is square root of temperature, our rule of thumb that the rate should double every 10 degrees doesn't work, for example. And so as the temperature is 10 degrees, the rate should increase as square root of, let's say, 393 by 383 degrees, not degrees, Kelvin. Then the square root of that ratio is 1.02, not double, not 2.0. So it's very clear that it just increasing the number of collisions is not sufficient to increase the rate, the extent we expect when you raise the temperature by 10 degrees. You could, of course, use some other numbers here, but it doesn't matter. It's just an argument to show that square root of T dependence is not what we are looking at. It is much larger than square root of T dependence. So our function has to be different from a square root function. That's what, of course, you all know the answer to this question, but anyway, I'm trying to show you where other, what other things one could look at and what might happen if you did this way or that way, right? And so a different explanation. What is alternative? A good explanation. There's also alternative. And so is like this. So A is in equilibrium with A star. So now we introduce a really important concept here. And this concept is so widely used. You could say it's a universal concept, and I will explain more detail why we say universal. So A is activated to give A star, even for unimolecular reactions. Or if you have A plus B, then A and B collide and give rise to activated species, A star, having excess energy in it. The star implies that it is not in a normal average energy state, but it has somehow acquired excess. This is a rich person among the population of the town. So the rich person then can afford to buy a car, and while others may not be. And so then that A star goes to product. And so this pre-equilibrium followed by a unimolecular or a single step reaction, there are elementary steps. There's a forward A to A star is an elementary step. And what that means is there is no other intermediate steps involved when you have an elementary step. And then A star goes to A. And then back, deactivates, A star deactivates to A. And so, or A star can go to product B. So the A star can decide, should I go this way or that way? Of course, it's all done by probability. That probability that A star goes to B is different from probability A star goes back to A. And so how is A star produced from A? Due to some collisions and other things happening. So what does this mean? This means equilibrium followed by a irreversible reaction. And this model is a very, very famous, as I was saying. And for example, if you go to entomology, Michaelis-Menten scheme is exactly this. If you go to absolute rate theory, this scheme is exactly this. If you go to protein denaturation dynamics, the scheme is exactly like this. If you go to Langmuir model and then try to explain what's happening in the adsorption process, model is this. And so it appears that this is a very, very fundamental chemical reaction or chemical mechanism, to be more precise. This is a mechanism that A goes to B, and the process involves this, A star and B. And A star, it may not be an intermediate. A star may live very short, and it may be your activated complex that you're talking about. And so it could be an intermediate in some cases as well. But this model of equilibrium followed by, so it's called pre-equilibrium, and equilibrium followed by a single step conversion to give rise to the final product. This is a basis for most of the chemistry, as I was saying. And so if you use that, then we can explain the temperature dependence. What that means is this equilibrium shifts with temperature. That we understand, right? We know that the equilibrium constant depends on the temperature, and then we raise the temperature, there's an effect of it. We can predict whether the equilibrium move forward or the equilibrium move backwards, and what the effect is, and quantitate it, and so on and so forth. So by introducing this equilibrium model, we're able to explain the temperature dependence. So anytime you're describing your rate as a function of temperature, you're making this assumption that there is a pre-equilibrium going to the product, particularly if it fits the model. If it doesn't fit the model, then of course, then that's not necessarily correct. And so what we do is now recall Boltzmann distribution qualitatively. So what the Boltzmann distribution is telling us is that as we move towards higher energies, then there is an increase in the fraction of molecules having higher and higher energies. And then that fraction drops off because there is the distribution function is product of two functions. One function is growing as a function of increase in energy. The other function is decreasing as you increase the energy of the system. And so when they multiply together, you get the total probability. And that probability is this distribution function, showing there is a maximum point where the maximum number of molecules will possess that amount of energy. Below that energy and above that energy, there are fewer molecules possessing that kind of energy. And so the number is varying. The energy is increasing steadily up to infinity. And what that means is, in this equilibrium model, that pre-equilibrium model that we are proposing, there is certain energy barrier. And those molecules that have energy higher than the barrier will pass through from A to B. Those that do not have that sufficient of energy will wait till they gain that energy. So the energy is obtained through collisions. So for example, only this fraction here of molecules. So if you integrate this area, you get the total number of molecules in this little area under the curve above the barrier. Those are the only ones that will react. But what happens is, once you take those out, the energy is redistributed, and some of them come back into that location. So this way, you can transfer most of the molecules that didn't have the sufficient energy to molecules that do have sufficient energy. Of course, you're expecting a thermal equilibrium with the bath. So the bath is going to provide the necessary energy to repopulate the missed states. And so the energy is continuously drained from the bath and then pumped into this, even at the same constant temperature, right? And then this fraction keeps reacting and reacting and reacting, and until the reaction goes to completion, and so on. So this is the key concept, and this is the key mechanism that we are talking about. So then, if you assume that reaching the saddle point on the surface is rate determining in the reaction sequence, so this is another assumption we make, and then this assumption valid for most of the reactions, and this assumption fails when you have quantum mechanical tunneling driving the chemical reaction. Yes, the tunneling drives chemical reactions in some respects and in some specific conditions. And so, except under those sets of conditions, the saddle point is the one that controls the rate of the reaction. Passing over the saddle point is the rate determining step in the sequence of events, which we call mechanism, sequence of events that lead reactant to the product. And so what that means is, in this situation, we have a saddle point. So only those that pass over the saddle point accumulate as products. They cannot go through the barrier. That's what we're saying. They go through the barrier, then that is quantum mechanical tunneling, and that has a different set of regulations, different temperature dependent. In fact, they're independent of temperature, those reactions. It's one of the characteristic hallmarks of a tunneling reaction, independent of temperature, because it's not going over this, and it doesn't have the same mechanism, it has a different path, etc. Anyways, so if you, as the fractional molecules have sufficient energy to cross the barrier, that's what determines what fraction can go over the barrier. That's the fraction that's going to react at any given time point. And so when we raise the temperature, what happens? When we raise the temperature, the curve shifts to the right. Means we are putting more energy into the system, and so there are more number of molecules that have enough energy to go over the barrier. So you can see that the area under the curve onto the right of the barrier line, this line is the barrier line, and more number of molecules are present in here. And so then more reaction will occur, more probability that they will go into the products, more of them will cross the saddle point, et cetera, et cetera. On the same point, you see less number of molecules on the other side, and the system broadens a little bit more than it was before. So as we increase the temperature, the system broadens. The maximum decreases. And these are the two things we looked at while looking at the Boltzmann distribution as well as the Maxwell distribution. This is very simple characteristics that are transferred over into the concept here. Now you see why we talked about all these distributions and distribution curves and probabilities, why it matters. So temperature broadens the distribution and shifts more molecules into the higher energy states. And so those states have the ability to go over the saddle point to give rise to the products. And so the lower temperature is like that in the blue, on gray, and the high temperature in this, the red and pink. And so that's the reactive fraction. And so this reactive fraction increases with temperature. So that's what is driving the temperature dependence, and not the collisions per se. Collisions are needed to do this, but the collision should have sufficient energy. Only then it will give rise to the product. So we ask, yeah, there's some probability the collision will happen, but what is the probability that that collision has enough energy to go over the barrier? So we have two different probabilities. You multiply them, only then you get the total temperature dependence. That's what we're talking about. So the Arrhenius equation is written classically this way, and we don't derive it, and it's not really derived. It's experimentally written out. K, the rate constant, is some constant e to the power minus E star over RT. E star is this famous activation energy you already studied and learned about. So A is your frequency factor, which we consider most of the time as independent of temperature. If A is dependent on temperature, then you do not see a linear fit, and then you see curvature in your fits. So in other words, if you plot log of A and K versus 1 over T according to this equation, right? If you take log on both sides, you will see that. Of course, you know that. It gives you a straight line, and with a slope equal to minus E star or 2.303, or that 2.303 comes in because of the ln to log conversion, natural log based conversion. And R is your gas constants. Again, the gas constant is so important, and I'm glad we figured out how we come up with the gas constant values in the under gases. So E star is the mysterious thing. So that's we are assigning to some barrier in the pathway that is giving rise to the product. And so the log of A is this intercept. And so that's the physical meaning, mathematical meaning of the frequency factor A. And it is actually associated with the entropy of the activation of the system. So somebody's asking, is anyone else cutting it out of, or is it my only connection? Kevin is asking. But so I would not know that. So if any of you experience the same thing, please let him know, because it seems that intermittent, the system is going in and out. Wow. Joe says it's working okay with him. I will wait if anybody else has things going in and out, let us know. Yeah, that may be a good idea to leave and come back. I will let you in. And let's see, where is, yeah, there, Kevin, okay. Let me see if anybody else is waiting. I don't see anybody else in the room.
That's a little bit better. You started sounding like a robot on my end, so.
Well, sometimes I am. Yeah, I don't see anybody else. Yeah, okay, so that's good. I'm glad we sorted that out. All right, so that's that. And so K and the frequency factor A are the unknowns that we are interested in when we measure the temperature dependence, but K is measured experimentally, and so we can evaluate A. And temperature is one that is the independent variable, and we plot log K versus 1 over T. The key point on that in the lab, one misses figuring out is the log of K means that K should have no dimensions on it. Only then you can take the logarithm for that. And so that's the key issue that one has to keep in mind. Means that you make the okay, dimensionless by using standard concentrations and dividing with standard concentrations, 1,000 moles per cubic meter and second. And so those are the units to be used. And I will show you an example how this is done. And that people get stuck with that in the lab when you try to do this. So that's that. And so in terms of mathematics, it's a pre-exponential factor. You determine it from the intercept. And in terms of concept, it is the entropy of activation. That's where we stopped the discussion. And so the entropy of activation takes into account what should be the value of A. It's independent of temperature, but not necessarily if you take very large range of temperatures. But for practical purposes, for 50 to 60 degrees is fairly constant for most of the cases. And in some cases, you do see actually curvature in this plot that I'm showing. It won't be linear, and it has lots of significance to it. And there are very few instances. We published about 30 years ago, something like that, 40 years ago, a curved plots, and then it means something very important. And so anyways, it's out of the ordinary. It doesn't happen all the time. And then, so we're going to look for a justification for this. Justification is like this: is you do a one-dimensional surface, potential energy surface. One dimension means that it only has X dimension, and that dimension X is the reaction coordinate. Means that the nuclei moving, and that whatever the nuclei moving, whatever that direction is, leading to product, that's the one we are picking as the X coordinate. And so in other words, you have reactants, you have certain geometry with certain energy in this well, and then you have that saddle point, and then you have a product in another well. And so I've written such that the products have higher energy compared to the reactants. And so the difference in the energy between the products and the reactants is the change in the energy of the accompanied by the chemical reaction. In this particular case, is endothermic. Means it could be, we could have written enthalpy here, then it will become delta H. You can write internal energy, then it becomes delta U. So we can write the G, and then it becomes delta G. So E is a general, symbol for energy used without specifying whether it's a G or H or a U. And so anyways, this is endothermic, where the products have higher energy than the reactants. And so the system is climbing steps. And then this climbing, in between, there is a higher point it has to reach before it comes back. So the E star is this energy barrier with respect to the reactants for the forward reaction. And that same E star will not be the same when system goes back. When the system goes back, the barrier height is different. And so the forward reaction has a higher energy barrier than the reverse reaction. You can see that. Here is an exothermic system where the products are at lower energy than the reactants. So when the reactants push over the barrier to the product, they're at a lower energy than the reactants. So this is the exothermic, and this is delta E or delta G or delta H. You can write all those different kinds of things, and then the shape of the plot doesn't change as you change the Y coordinate parameter. And so this is easy now to understand if this is the case. So the system needs certain energy to go over the barrier, and this is well beyond the collisional barrier. And so it has to have energy to break the bond partially. That's the chemical concept. So if I want to break a bond, it has to go through the saddle point where the bond is stretched enormously. And it is now achieving a weird state, very unstable state. And then from that, you can go back to the reactants, or you can go forward to the products. And so we're now going to introduce this concept of activated complex and transition state and things like that. And so these are key parameters we talk about in reaction dynamics. And so this highest energy state is called the transition state. So state means a certain energy level. So we don't refer to the structure here. We only refer to the energy state. So the reactants go to that point, and then from there, they go down to that point. And so the highest energy state is the transition state. And then this transition state has certain structure to it, right? Because it has nuclei, there are certain distances between the nuclei, and therefore we can use that as a sort of a chemical entity. And that chemical entity may have stretched bonds or twisted structures and or complicated geometries. And so that's why it has higher energy than the reactants. But they can fall either to the reactants or to the products. So what we are saying here is the energy state is the transition state. The chemical structure is the activated complex. So these are very two different entities. And in a lot of the time in the literature, you see that these are interchanged constantly, and that's not right. And that's because maybe they didn't take the chemical kinetics course. But anyways, then the intermediate is that you go through a state where there is actually a minimum, local minimum associated with it. And here there is no minimum. It's a maximum goes back into the reactant or to the forward to the product. But here it can survive for a while, and this is an intermediate that is produced. So this is different from the activated complex we talk about. So the organic chemists talk about a lot that, oh, you make this intermediate and then it goes this way or that way. And so here instead, so we are concerned with the transition state and the corresponding chemical structure called the activated complex. And so